Welcome everyone. Today I'm going to be talking about meso compounds. So, in under half a minute, here is a summary of this video. First, we're going to go over what a meso compound is. We're going to go over the characteristics and some things to look out for. Next, we're going to run through some examples to identify whether a compound is a meso compound. And finally, I will provide you with two molecules to determine for yourself whether they are meso compounds. If you're new here, my name is Liah, and on my channel you can find science and math videos. Alright, so what is a meso compound? We have 5 things that we're going to identify with them. So, number 1, is a meso compound achiral or a chiral molecule? Well, it turns out that meso compounds are achiral molecules. Now, for the second part, how many chiral centers are needed for a meso compound? Do they need none? Do they need a few? How many do they need? Well, it turns out that meso compounds have an even number of chiral centers. So it could be 2, 4, etc. Okay, they just have to have an even number of chiral centers. Now, are meso compounds optically active or optically inactive? That is, do meso compounds rotate plane polarized light? Well, we know that achiral molecules are optically inactive. Therefore, meso compounds are optically inactive. Meso compounds will not rotate plane polarized light. Now, for the configuration of these chiral centers, what is required? We know that there are going to be chiral centers on the meso compound, but what is the specifications for these chiral centers? Well, it turns out that if, for example, if you have 2 chiral centers, one chiral center needs to be S, and the other is R. The other needs to be R. Okay, so this means that if you have 2 chiral centers, you need one of them to be S and the other to be R. If you have 4 chiral centers, you need 2 of them to be S and the other 2 to be R. You need the number of S chiral centers to be equal to the number of R chiral centers. In this way, they will cancel each other out, making the entire molecule achiral. Now we are on to the 5th characteristic of a meso compound. Now the 5th characteristic is that on these chiral centers need to have matching groups. Alright, so we know that they are chiral centers, so each carbon will have 4 different groups, but when we compare the chiral centers to each other, they need to have the 4 same groups. They need to match. So we'll just put here, they need to have matching groups. If one of the chiral centers in the meso compound is bonded to groups A, B, C, and D, then the other chiral center in the molecule needs to be bonded to the same thing. If the other chiral center is bonded to something different, for example, A, B, C, and E, these 2 chiral centers do not have matching groups, and therefore the molecule would not be a meso compound. If you are looking for a meso compound on an exam or quiz or homework, you should be looking for these things. You need an even number of chiral centers. You need to make sure that the configuration of those chiral centers oppose each other, and you need to make sure that the chiral centers have matching groups. That is, they are bonded to the same 4 groups as the other. So these are the 3 things that you need to be on the lookout for when you are looking for a meso compound. Using the characteristics we have outlined before, let us determine whether this is a meso compound. Well, what does a meso compound need? It needs an even number of chiral centers. Even number of chiral centers. These chiral centers need to have matching groups. And these chiral centers need to be, one needs to be R and one needs to be S. So 1 R chiral center and 1 S chiral center. Well, let's see if that applies. So if we do this, let's check that we have an even number of chiral centers. Our chiral centers are right here, 1 and 2. We have 2 chiral centers, so this first one is satisfied. Let's go on to see if they have matching groups. So this carbon over here has a CH3, a chlorine, a hydrogen, and the rest of the molecule over here. You will notice that looking at this chiral center, this one is bonded to a CH3, a chlorine, an applied hydrogen, and the rest of the molecule. So yes, they have matching groups. Now we need to check whether one chiral center is S and the other chiral center is R. So let's assign R and S to these chiral centers. So assigning these by atomic number, remember that the atomic number is going to determine whether that is the first priority or second priority or third or fourth. So chlorine with the highest atomic number is going to be priority number 1. Next we have priority number 4. There is nothing with a smaller atomic number than hydrogen, so that is always 4. Then we have 2 for the rest of the molecule and 3 for the methyl group. Now ignoring the dash, we're going to see what this appears like. This appears like 1 to 2, 3. This appears to be R. And because an even number is on our dash, this configuration stays the same. So this chiral center does indeed have an R configuration. Now let's check the configuration of this one over here. So this one, chlorine number 1 priority, hydrogen number 4 priority, then 2 for the rest of the molecule, and 3 for this methyl group. So covering up the one on the dash, we count what's left. So 1 to 2 to 3. So this appears to be R. Now what is on the dash? Well, it's an even number. And so this configuration that we just got stays the same. So this chiral center right here is indeed R. Now remember, for a meso compound, we need one chiral center to be R and the other to be S. But here we have both chiral centers as R. Therefore, this is not a meso compound. So this criteria was not satisfied. A second way of looking at this is that for this molecule, if you put it in this kind of tabletop format, you will not have symmetry. So for those of you who are basing your answers on symmetry or dealing with that, this is not symmetrical. One is wedged and the other is dashed. Now, how did I know how to rotate this? Well, if you flip this bond right here down, like this, then you must change the wedge to a dash. So that's a neat trick that you can use. But by our definitions and our criteria here, we have determined that this is not a meso compound. So if you don't like converting it and rotating the bonds here, you don't need to. You can simply follow what we just did. Now let us do another example. So is this compound a meso compound? So again, we're going to write our criteria, so even number of chiral centers. We need to have matching groups on those chiral centers, and those chiral centers need to be, one of them needs to be 1R and the other needs to be S. So take a moment for yourself and determine whether this molecule is a meso compound. Alright, so let's start. We're going to check each one of these criteria as we did before. Does this compound have an even number of chiral centers? Well, it has 1 chiral center, 2 chiral centers. That is an even number of chiral centers, therefore, this criteria is satisfied. Let's check the next. Are these chiral centers bonded to matching groups? Well, let's check. On this one, we have a bromine, a hydrogen, then we have the carbon over here that is bonded to the bromine and hydrogen, and then we have the other group that is CH2 and goes on to a C down here. Let's check this chiral center. This chiral center is bonded to a bromine, a hydrogen, then going over here we have the carbon with the bromine and hydrogen, then going down here we have the CH2 and then the C down here. So yes, these two chiral centers have matching groups. They have the same groups on each chiral center. So this criteria is satisfied. Now let us check for the configuration. Let us see if one chiral center is R and the other is S. We're going to start right here, determining R and S. Bromine will have priority number 1 because it has the highest atomic number. Then we go hydrogen 4, and then we're going to go 2 over here and 3 over here. So ignoring what's on the dash, we see that we have 1 to 2 to 3. This appears to be R. So this chiral center has an R configuration. And because the even number is on the dash, we know that we can keep our configuration as is. We don't have to change it. Let's check the configuration of this one. So we have, again, bromine number 1 priority, 4 for hydrogen, 3 for the rest of the molecule, and 2, again, going towards the carbon with the bromine. Ignoring the dash again, we have 1 to 2 to 3. This is going counterclockwise, which means this chiral center is S. Now let us check what's on the dash. What is on the dash? It's an even number, so this configuration stays the same. Now we see that one chiral center has configuration R and the other one has S. So yes, this last criteria is also satisfied. Therefore, this compound is a meso compound. Now here's a Fisher projection. See if you can determine whether this is a meso compound or not. Alright, so I have written down our criteria here. Now let us see if we have an even number of chiral centers. Turns out we do. We have a chiral center right here. These are carbons. Okay? And these are chiral centers because they're bonded to 4 different groups. So yes, we have an even number of chiral centers. Now matching groups. Let's see. The top part is attached to an OH, that's CH3, a hydrogen, and the rest of the molecule going down here. Now, how about this carbon? This carbon is attached to an OH, a methyl, a hydrogen, and the rest of the molecule, which matches this part. So yes, both chiral centers have matching groups. They are bonded to the same groups as each other. Now let's determine R and S, because we need to decide whether it satisfies this criteria. So let's see. Let's start with this one down here and assign priorities. So again, oxygen has higher atomic number, so it's priority number 1. And we will go to the rest of the molecule, number 2. And then we have 4 for hydrogen and 3 for methyl. So let's ignore hydrogen. This is what we do for Fisher projections. We ignore the hydrogen and we count what's left over. What is left over? Well, we go 1 to 2 to 3. This appears to be S. However, because hydrogen in this Fisher projection is on a horizontal line, we need to switch our configuration, S to R. So it is not S, but it is R. For Fisher projections, you need to remember to change your configuration if the hydrogen is on the horizontal line. Now let us check the configuration of the second chiral center. Well, we have 1 for the OH, 3 for the methyl, 4 for the hydrogen, and 2 for the rest of the molecule. So ignoring the hydrogen, we have 1 to 2 to 3. This appears to be R going clockwise. Now let us check. Here we have the hydrogen on a horizontal line, so we must change R to S. It is not R, but it is S for this chiral center right here. So let's decide. Do we have one chiral center that's R and one chiral center that's S? Yes, we do. We have these satisfied. So this Fisher projection is a projection of a meso compound. Is this a meso compound? Just looking at it, right, we need an even number of chiral centers. I'll just put CC for chiral centers, and then we need to have matching groups. And we also need to have one of the chiral centers be R and the other chiral center to be S. Are there chiral centers on this molecule? It turns out that there are no chiral centers on this molecule. Yes, there's a methyl. Yes, there's a hydrogen, but when you start comparing these for difference, you end up intersecting at this carbon, and if you intersect, that is not going to be a chiral center here. Can't intersect. You can't end up at the same point. So they tied and tied and tied until they met. So without chiral centers, right, and the same story goes for this one. They would, let's see, if you're trying to decide here, yes, there's a methyl, yes, there's a hydrogen, and then if you go On here, you have a CH2, they tie, so you need to go on and eventually you intersect right here. So there are no chiral centers. Therefore, we know right away, without doing any other work, that this is not a meso compound. Because there are no chiral centers. Now try this one on your own. Is this a meso compound? Alright, so let's go ahead and start this. Do we have an even number of chiral centers? Yes, we do. We have, let's use a different color, this carbon here and this carbon here are indeed chiral centers, and I will draw in the implied hydrogens. Okay, so this one is that we do have an even number of chiral centers. Do they have matching groups? Yes, they do. Each has a fluorine, a hydrogen, a methyl, and the rest of the molecule, which they match over here. Okay, so going over here matches going over here. Alright, so yes, they have matching groups. Now we need to determine R and S to see if they fit the last criteria. So let's assign priorities. So for this first one, we have hydrogen is number 4, last priority. Fluorine is first priority. The methyl group is going to be third priority, and the rest of the molecule going to this carbon, attached to the fluorine, etc., is going to be priority number 2. So let's ignore what's on the dash and count what's left. So we're going to go from high to low priority, or from low to high number. So 1 to 2 to 3 appears to be R. What is on the dash? It's an even number, therefore we can keep this as R. Now let's find the configuration of this chiral center. We have fluorine as first priority, hydrogen as fourth priority, methyl as third priority, and the rest of the molecule as second priority. Let's ignore what's on the dash and count the numbers that are left. So going from 2 to 3 to 4 is a clockwise and therefore R configuration. Now remember, we need to check what's on the dash. What is on the dash? Well, that is an odd number, and therefore we need to change R to S. So this chiral center is not R, but S. Now let's check if these are opposing chiral center configurations. One is R, the other is S. Yes, so it does fit this criteria, and therefore this is a meso compound. Here's another one for you to try. Is this a meso compound? Does it have an even number of chiral centers? Well, here's a chiral center right here. Right, it's the bromine, the hydrogen, the methyl, the methyl here, and the rest of the molecule over here. Now over here, what's going on? Well, over here, this carbon right here, I'll do it in green, is bonded to CH3 here, CH3 here. We automatically know, without doing anything else, that a carbon attached to 2 of the same group, this 2 methyls, this means that this carbon is not a chiral center. So we only have one chiral center, and we need an even number of them. So this is not going to be fulfilled. Therefore, we can say right now that this is not a meso compound. Okay, it just doesn't satisfy this first one. So we don't have to do anything else. We automatically know from doing this, from counting the number of chiral centers, that this is not going to be a meso compound. Now it's time to check your progress on your understanding of meso compounds. So I have given you 2 molecules. Go ahead and write them out and go through the steps we did. So find if they have an even number of chiral centers, find if those chiral centers have opposing configurations, and find if those chiral centers have matching groups. You're more than welcome to leave your answer in the comments. Thank you so much for watching, and I will see you next time.